Hey, in today's session, we learn a little more about the concepts that we learned in our last session, which was about simple linear regressions and their properties. Through this lesson, we'll primarily learn two sets of things. One, Theorem 2.3, which is unbiasedness of error variances. I'll tell you exactly what do we mean by error variances in a little bit. Essentially, standard error. And then second, concepts. Now, these are concepts associated with a few transformations that we usually do, but this turns out to be extremely helpful as I've done both of them across the, the basic research that I've done so far. Firstly, let's talk about the theorem. Unbiasedness of standard error or unbiasedness of error variance. When we talk about standard error, we essentially say that we're talking about the standard deviation of the beta coefficient. But you'd say that, hey, Sarthak, if you're doing the same regression, how do we have a standard error? It's based upon the fundamentals that if we repeat it over and over and over and over and over again, the same type of regression, you eventually get to a beta coefficient that ranges across certain degrees of values, but eventually it consolidates down to a normalized form. Over here, and I'll work through this data code after this, but you see that when we're working at 500 observations for a given regression, I've particularly normalize this so that it's easy to understand. You see that your central tendency ends up falling around the 10 value on the x-axis. Similarly, when you look at 1,000 observations, or when you increase the size of the data, you have a leaner range of variation that you work with, but eventually your central tendency remains to be at the same level. So what do we mean when we say that the standard error of a coefficient is X or Y? We are essentially trying to say how precise are we in terms of our beta coefficient. So imagine if I tell you that your beta coefficient is 1, but your standard error is plus minus 2, that is, it ranges between 3 and negative 1. And I ask you to create a hypothesis out of it. And your first response would be, "Stop, okay, hey, I cannot really make any observations because yes, while I have more than one standard deviation set across the positive line of the axis, I still have certain values in the negative side. So that way, I'm not able to make any observations or core conclusions on the data. And hence, standard error is important. So what standard error then gives us is confidence intervals. When we get into further concepts, it also helps us understand something called the z-score. Essentially, is our is our hypothesis, or is the data analysis that we're doing proving our hypothesis, i.e., is it proving the null hypothesis right or wrong? We'll get into this later, but essentially understand the concept of standard errors. It is essentially the standard deviation of beta coefficients when regression is repeated across multiple amounts of times. Let's look at the graph over here. First, we have a graph with 500 observations. Then we have a graph with 1000 observations. You'll see that for 500 observations, the graph is a little more wider. For 1000, it gets leaner. But there's one thing in common. The central tendency more or less ranges around 10. And this is because we've done our y is as a function of 10x. I'll get into this data code soon. But essentially, what we see is that as you increase the number of observations, the central tendency becomes more and more accurate, and data becomes slimmer and slimmer in this process, indicating that accuracy actually improves when you have higher number of observations. There is a formula attached to it, not extremely important, but still good to remember, as this will give you an insight into what really we are talking about. The sigma that you see over here in point 2 and 3 is the variance of the dependent variable, is the variance of the dependent variable, and hence what it tells you is that the standard error is actually a function of the standard deviation and SST. Now, what do we remember about SST? SST is essentially the total sum of squares, which is the difference between the y value and the y predicted value. And then when you put this into a formula, you get this standard error of beta 1. Similarly, when you do it for beta 2, you get that, beta 3, so on and so forth. Perfect. Now, on this particular screen, you'll see that what I've done is that I've run a couple of lines of code. essentially to create a data set that helps us understand this concept of standard error and unbiasedness. Firstly, what I've done is that I've set 500 observations for every iteration. For every iteration, I've created about 500 such iterations where x is equal to a normalized range between 0 and 1, y is equal to 1 plus 10x plus r normal, again, which means normalized between 0 and 1. And then I've run a regression, absorb those values, and develop a histogram. So when I execute this code, it gives me something that looks like this. What does this tell us? It tells us that when you plot all beta coefficients together, beta 1 coefficients together, eventually has a central tendency around the value 10. However, when you look at the normalized curve that I've applied over here, you'll notice that essentially this follows the same path as the normalized curve. So regardless of your central tendencies, which is 10, which gets satisfied, you have the values ranging between this particular area. And this is exactly what gives rise to your Z score or your T score, or something like that, T statistic. This way, you're able to predict how accurate or how confidently you can tell whether the regression that you've run is accurate or not. Perfect. Now, I hope that that concept is fairly clear to all of you. We'll move on to the next concept of log transformations. Three, two, one. I hope that that concept is fairly clear to you all. Now, what we move on to is log transformation. Log transformation is essentially done in order to capture certain variables that might be otherwise difficult to interpret. So, for example, we're talking about house prices in California. In California, house prices can range from anywhere between $300,000, for example, to $15 million. But imagine working through all of that entire range of data set to understand what exactly happens when you increase, let's say, the size of the house by 10 square feet. It becomes a big question that is very difficult to answer given the magnitude of data that we're dealing with. And hence, when you have such a high magnitude of data, you use something called log transformation. There are different use cases for this, anyways, but log transformation is extremely helpful in those scenarios. Now, let's look through this table. This table is fairly self explanatory, but what it does tell you is a lot about how can we interpret certain values in this process. When you perform a log transformation to a dependent variable versus an independent variable, it has different impacts. And in order to assess them and interpret them best, it is important to just learn and memorize this table. It is not very complicated, but just memorize it. It'll serve you well in the long run. Let's talk about the dependent variable being continuous, which is it ranges between the 200,000 or $300,000 for the California house prices to 10 million. That's the continuous range. And then you've got independent variable, which is also continuous. So now let's think about this as square feet. So this can range from 1,000 to 10,000. So when you say that when you run a regression on this and you interpret as a one a 1 square feet increase in the size of the house leads to an X dollar or leads to a beta 1 amount of increase in the price of the house. So that way you've got your independent variable being continuous, which ranges between those values, dependent variable, which is the price of the house, also being continuous, and that way you get some value. But think about it. Is it really easy to interpret what impact would 1 square feet or 10 square feet or 100 square feet would have on the exact house? It is possible, but we'd love to know a little more intuitively regarding what's going on. Now let's look at the other one, which is your dependent variable is a log transformed value. Your independent variable is a continuous variable. In other words, we've turned the prices of the house into log form, and the independent variable, which is the square feet size of the house, still remains as its pure continuous variable value. And hence, what you get is that when you run a regression, you get that 1 unit change in x leads to 100 times beta 1, whatever that coefficient value is, percentage of change in y. So your beta 1 value would generally be point something something, And then when you multiply it by 100, you'll get the exact percentage change due to a change or an increase in x value. Then let's look at continuous and log. Here we're assuming that the dependent variable, which is the price of the house, is a continuous variable. The size of the house, which is in square feet, is in the log form. And hence, this can be interpreted as a 1% change. Now, here's where we've changed the dialogue. We're talking about a 1% change in x leads to a beta 1 by 100 change in y. And here we're talking about a pure value transformation. So beta 1 by 100 would be the exact pure value change in y due to a 1% change in the value of x. So let's say you've got a 1,000 square feet house. We say that if we increase the size of the house by 1%, that is, get it up to 1,100 square feet, it leads to the price of the house to increase by beta 1 divided by 100 change in y. So it's a percentage implies a pure transformation. Lastly is log transformation. Here's where we say that 1% change in x leads to a beta percent change in y. What this essentially means is that if we transform both values, the price of the house and the square feet size of the house, into log values, you eventually get a 1% change in the size of the house in square feet leads to a beta 1% change in the price of the house. And that way, you're able to really transform the values that you have and turn them into log variables. Last, we have dummy variables. Now, in dummy variables, there are two things or perhaps three things that we can essentially do. We can use a dummy variable as a dependent variable, dummy variable as an independent variable, and dummy variable as an independent variable, but to differentiate through categories. This is a larger topic, the third part that I mentioned, and hence we'll get into it a little later. But when you use dummy variables as a dependent variable, you're essentially trying to calculate probability distribution. When you use dummy variable as an independent variable, you're essentially trying to capture the impact of an event or impact of a sudden change in, let's say, a qualitative factor of life. For example, when you use dummy variables as dependent variables, you're looking at, let's say you're playing poker and you have the cards that you have in hand and you have collected all the data together and you want to estimate what's the probability of me winning $10. So by assigning 1 as winnings above 10 as 1 and winnings above 0 as 0, you use that dummy variable and regress it on the cards, the collection of cards that you've had. And then it gives you a probability based on the current collection of cards that you've received. And that way, the dummy variable really spits out the value or the probability through which you're likely or unlikely going to win or lose money. Second is when we want to capture an event. Let's say you're trying to let's say you're trying to understand the impact of COVID-19 on your family savings and incomes. In that process, what you do is that you regress, you've got all the data, let's say your parents' income, the stock market, your income, your sister's income, if your dog earns money, why not, your dog's income, and so on and so forth. Then you add a dummy variable at the end, which says 0 for non-COVID periods, 1 for COVID related period. So that area falls into, let's say, November of 2019 to June of 2021. That range, by assigning that dummy variable, you're essentially able to capture what was the impact of COVID-19 on your family's incomes and savings. Now, I'm not saying that the regression will be valid, but on a high level, this is how we'd use a dummy variable. Lastly, or perhaps the second and a half point, is when we use dummy variables for categorizations. Let's say there are four options you have that you choose from and try to estimate a dependent variable. I'm not really able to think of an example, but in that case, you assign three dummy variables for each of those categories and leave the fourth one out. That eventually spits out the probability of something happening, or the differential probability increase due to a variable being dropped. It's a little more complicated. I'll get into this in the next video. But essentially, this is what dummy variables do. It captures information in a binary form and helps you understand the effect of an effect of lack thereof of that particular event, situation, or probability. Thank you so much for sticking through the video. I hope you have a nice week ahead.